Hello, linear algebra student. This video is for chapter 2.3 part 1 about inverse matrix. So in this video, we'll talk about, or in this chapter, we actually investigate some of the features of of invertible matrix. And as a result of knowing an invertible matrix, we have a lot of things that is equivalent to it, namely how it relates to linear transformation, when A is actually the matrix of transformation, and how it relates to A being the coefficient of matrix of a matrix equation, etc., etc. So it actually is a very important theorem that links matrices, vectors, everything that we have learned since chapter 1. So it's kind of like the finale of everything that we have learned. And knowing that a matrix is an inverse, has an inverse, actually is equivalent to a lot of other things. And so we're going to talk about the properties of an invertible matrix. So remember in chapter 2, when we talk about inverse and all those, this matrix is not an augmented matrix, it's the coefficient matrix, and in particular, it's coefficient matrix of a square matrix. Okay, when we talk about inverse, it has to be a square matrix. Whereas when we talk about usually just a linear transformation or any systems equation, it would not be. So this only apply if it is an n times n matrix. So first is what is the details of this invertible matrix theorem. So we have from A to L statements, and all these statements are actually true together. That means A would imply B, B imply A implies C, C also imply A. So the way we prove it is, some of them was proved in like chapter 4 about like A has an prefix n prefix position, then the AX equal to 0 has only the trivial. I think it's chapter 2.1. So some of them are proved in, no, the one that's proved in chapter 1.4 is like the equation AX equal to B has at least one solution, then AX. Oh, then A has an n perfect position. So this has been proved in other area. So we're just linking them together. So, but in order for them to be all equivalent or they're all true at the same time, the books talks about the proof in several circle. So namely, the way we look at it is we don't prove A to B and B back to A like this. It's actually a proof in A to J, then J to D, C, B, A. So let's talk about it. A is, just read it through it first. A is an invertible matrix. Then we can say there is a matrix C, which is A inverse, such that C times A is equal to I, right? So that is A to J. And if J works, then we have D. We can solve the equation AX equal to 0 only have the trivial solution because A times X. So for D, C is the inverse, so we would say C A X will equal to C 0, and this is I, so I X is equal to C 0. So X is equal to 0. 0 times anything is 0. So this is the only trivial solution, right? So, and then from D, so you can see the circle. From D, we can say C. If it only have a trivial solution, then it must have n perfect positions. So there's no free variable. And then it would go back to B. If it has n perfect position, then it could be row equivalent to n times n identity matrix. Right? Perfect position means it has 1, 1, 1, 0, 0, 0, all those. So back to B, and then B, if it is row equivalent to n identity matrix, we know actually the definition or the way we make an inverse is through the row equivalent to an identity matrix. So that go back to A. So there is a loop of A to J to D to C to B to A. So all these 5 are equivalent. Then the second loop is link everything together through A again. So from A, we can go from K to G. K is the other inverse, right? K is the other, let's say AD equal to I. And then go to D is AX equal to B has at least one solution, because if AD equal to I, and then AX equal to B, then we can say that the D is the A inverse, right? And if the D is the A inverse, then we have AD equal to I. Okay, so we will say I. Hello, linear algebra student. This video is for chapter 2.3, characteristics of invertible matrix, and it is called the invertible matrix theorem, IMT. It's a very famous theorem because it basically wraps up everything that we have learned from chapter 1 to up to now, chapter 2.3. You can think of it as kind of like the halfway of everything that we have learned. So we learn about matrix, we learn about vectors, we learn about transformation, and these actually talks about the fact that if you know the coefficient matrix of linear system, which is equivalent to a linear transformation standard matrix, then there are a lot of things that ties together. They're all equivalent, especially if it is invertible. And the opposite of IMT also say if one of them is not true, then none of them is true. So you can use it as the negation to know a lot of stuff about transformation and everything. So to prove this, let's read the A to I statement. So these statements are all equivalent. If one is true, all the others is true. So the first is A is invertible. And then we actually, in the last section 2.2, we already know that A would be row equivalent to an n times n identity matrix, because you can actually, through elementary transformation, elementary row operation, to convert your matrix into a identity matrix. And then also it just means that it has n perfect position because of the identity. And if it has n perfect position, so AX equal to 0, we have only the trivial solution, and we can prove it by actually starting from K back. Okay, and the next one is the column of A would forms a linear independent set. The linear transformation is 1 to 1. These we proved in 1.9, 1.9, 1.10. No, I think chapter 1. Equation AX equal to B has at least one solution for each B. The column A span Rn, so this is 1.4, right? When we're looking at the matrix equation and also about span. And I is the linear transformation from X to AX maps Rn onto Rn. That means for every B, you can actually have a X that maps to it. And there is it also means that you can find a matrix such that, matrix C such that C times A equal to I. And you can find a matrix D such that A times D on the other side is equal to I. The last one is A transpose is also invertible, which we cover, I think, in 2.2. So first of all, to prove these, we don't have to prove every single equivalency. The way to do it is form some loop. So if A imply B, B implies C, like that, and then loop back. So the loop is not like that loop. The way the book does would be they do it through 3 loops, or 3 or 4 equivalency. So first is a big circle from A, J, D, E, B. Okay, A, J, D, E, B. So A is an invertible A matrix. So invertible means A inverse exists such that A inverse and A would become I. And so, of course, you can find C because C is A inverse, so it becomes I. So this is kind of like the definition, right? And then AJ what? AJ, and because it's you can find that, then we go to D, which is A x equals 0 has only the trivial solution. So that's very easy to prove because to solve AX equals 0. But then we know that CA is equal to I exists. So we just multiply C on the left-hand side. So CA is equal to I. So this becomes I times X is equal to C times 0. I times X is X. C times 0 is 0. So this is the solution. Solution is 0. It's only the trivial solution. So this is D. And then from D, we can prove C. C means it has n prefix position. Anytime you have a unique solution, you would have n prefix position. Okay, and then D, that means, and then C after C you go back to B, which is if it's n prefix position, then you can row equivalent to n times n equivalent identity matrix, and that means is going back to the fact that it is invertible. So this forms a loop. And then the second loop is AKG. A is an invertible matrix. Then you can find a matrix D such that AD equal I. And this matrix is A inverse because by definition that is the inverse invertible matrix. AK, and then we go from K to G. Whereas G is the equation has at least one solution. How do I know that? So from G, we would say AD ADX would equal to ADB would equal to B, right? Because this is I. We know that AD equal to I. But then ADB by associative property is ADB equal to B. So that means if I have an equation that I want to solve, one of the equation, once there is at least one solution for X is equal to D times B, right? So at least we have one. Maybe we have more. We don't know. So that means I have at least one. So that's one loop. AGK. And then from G, you would have the equivalency of H and I through the old stuff, right? Once you prove that, one solution, then this is 1-to-1, and also linear dependence, that is from chapter 1, the later part of chapter 1. And also from D, you would have DEF. D is the equation has trivial solution, it's linear dependence, and it is also 1-to-1. So that is earlier in 1.4. And then we also do L, which we cover in 2.2. Is A is invertible matrix, then A inverse is also invertible, right? I don't know if I prove it, so how do I know that it is also an invertible matrix? So we claim that there is the invertible matrix is A inverse transpose. Is the inverse of A transpose. So how do I prove it? I would say I'm going to multiply these two together, right? To say that it's supposed to be equal to 1. And last time we say if we have two product of two transpose is the transpose of two products, but in reverse order. So we'll just reverse them and transpose them. So once we A times A inverse inside is just I transpose is also equal to I. So you can see that these two multiplied together is a identity. So the A transpose inverse is A inverse transpose, so it is invertible. You can find a matrix